Well, okay, let's start. Good morning. So today I would like to mention the two other consequences of the mean value theorem that I think are important, immediate consequences. Remember, I had mentioned three of them. First of them was that if you have a C1 function, then all partials exist and are continuous, and vice versa. That is to say, you get to assemble all partial derivatives insofar as they are continuous functions into one big total derivative, and that would give you the derivative of the function. This approved last week. Second consequence is that if you have a twice differentiable function, or if you have a C2 function, doesn't really matter, insofar as you get to differentiate 2 times, second order partials should commute. That is to say, partial x, partial y should be the same thing as partial y, partial x. I'm going to give you a more rigorous statement here for this theorem. I'm going to give you an idea as to how to prove it as well, but we're not going to prove it. Third, Taylor approximation. Again, I'm going to give you one statement of this Taylor approximation. I'm not going to prove it. I'm going to give you an idea as to how one can prove it. And after I state these two statements, I'm going to switch over to an example. Again, we're going to take a polynomial function and do some explicit calculations, because at this point, I think it would be a lot more useful for you to have a sense as to how these things operate. Okay, so I'm going to be taking attendance today. Are there any questions before I start? Okay, so let's start with this. And this is sort of the easier way to remember it. Here's a much more detailed way of stating this. If I have, let me again recall that we have the usual standing assumption. M is a subset in E. E is a normed vector space. N is a subset in F. F, again, is a normed vector space. And I'm looking at functions that go from M to N, typically. And so this Clairaut-Schwarz, and some people also attribute it to someone called Young. There's like 5 billion people who proved this apparently, probably in different situations. If the input space is a product, so that I can talk about partials, and f from m to n is such that all first partials exist, so d1f and d2f exist in the sense that we discussed last week. And let's say, well, d1f itself has a second partial, and it is continuous. Let me just check my notes. Yes. d1f, d2f, so these are the first partials, horizontal partial, vertical partial. And let's say d2, d1f. So this is the second partial of the first partial. Exist, and the latter one is continuous. So when you think about the type of this, d1f, right? So f goes from m to n. Let's keep track of the types. d1f is going to go from m to bounded linears from the horizontal components into f. Which means that if I were to take the second derivative of this function, so d2, d1f is going to take values in bounded linears on E2, taking values in bounded linears on E1, comma f. And using this multilinear business, we can just write it like so. Bounded bilinear E1 times E2 in f, or into f. This latter function is continuous. then d1, d2, so partials in the other way around, also exist, and in fact they are equal. Exists. And d1, d2f equals d2, d1f. In a similar fashion, you can show that if a function is twice differentiable, so similarly, let's say this is the first part. Second part, if f from m to n is twice differentiable, twice differentiable, then for any x in m, the second derivative is supposed to be a bounded bilinear. Again, let's record this. The types. So if f goes from m to n, f prime is supposed to go from m to bilinears from E to F. F double prime then should go from M to bilinear E, bilinear E, bounded linear E, bounded linear E, F. But then we said that this we can combine as bounded linear taking two values, so bounded bilinears. And so I'm thinking of f double prime of x as a bounded bilinear operator. This is symmetric. And the problem set due this Friday, you're going to work on symmetric, and there's another version, alternating bilinear or multilinear operators. This just means that it doesn't matter in which order you feed these two vectors in. So this means that f double prime of x at h comma k is the same thing as f double prime of x at k comma h. And of course, by induction, I can do this with higher order derivatives as well. I'm going to leave that to you. Now, I just graded, I think, problem set 5, where I was asking you to compute the derivative and then the derivative of the derivative and so on. And I was generally very happy with you guys being able to compute this f prime. I should still let you know that, as usual, I wrote down the solutions. I took my time this time, wrote very detailed solutions. I would highly recommend that you go check out my solutions as well. And after I read this, your solutions, I realized some of you are familiar or comfortable with this idea of the Hessian. So it's a certain matrix that you can associate to the second derivative, at least insofar as your function is defined on a set of tuples and it's taking real values. In terms of the Hessian is always a square matrix. This says that the Hessian is a symmetric matrix. Okay. So Hess of f is symmetric. Symmetric in the sense of linear algebra. Symmetric. Okay. This is the first statement. I'm not going to prove this, but I just want to give you an idea as to how one typically proves this type of things. And you can have a look at the proof in the textbook. And in the textbook, they just do it for functions defined on R2 taking real values. But in fact, the same proof applies essentially in this more general setting. The surprising thing in that proof is a certain function, lambda, that they use, okay? And they don't really give, or our textbook doesn't really give that much of an idea as to why you would look at that function. So I just want to give you a sense as to why that is sort of the natural choice. So idea of the proof. Well, I'm going to fix a base point as usual, x, which is x1, x2. And I'm going to take a vector, h, which is an E. So in the textbook, they define this function called lambda of h1, h2. And they define it like so. So textbook. Okay. And it's this function. You fixed x1 and x2, and you have a small perturbation h. It has the x component, or the horizontal component, and the vertical component. And then, essentially, you do something with this function. Did any of you see something like this before? Or are you familiar with perhaps looking at this? So I was like that too when I first saw this proof many years ago. I was like, where does this come from? Why am I looking at this function? I mean, I understand that in the proof it works, but I like the types of proofs, or I like the types of exposition that makes me feel like I could have proved it, I could have come up with the proof myself. And so this is, in fact, what is called a second order finite difference. So there's a whole area of mathematics. I guess you can call it finite element methods. This is especially important in numerical approaches to differential equations. And so you say, okay, theoretically we're sort of like taking these limits and stuff like that, but when it comes to simulations, and when it comes to trying to compute things using a computer, there's no such thing as an actual limit. And so what they do is, instead of taking that limit that defines the derivative, they just take h to be sufficiently small and they keep it small. And so instead of looking at the limit, which is this infinitesimal object, d1f, d2f, whatever, they have a finite step approximation to it. And so here's the idea. So far, we were defining differentiability of f at a point like so. Right? So this is the function I'm trying to approximate. And then I have here the first order approximation. So this is an E. And then I'm going to take the limit as h goes to 0. And this was the idea of the derivative. Well, to figure out, to make sense of this expression, instead of putting the parentheses here, you put the parentheses here. Okay? So instead of looking at it like this, I'm going to delete this. Now I need to distribute the minus. Minus, like so. And this, you see, it's a linear operator. It's a linear function of the function f itself. And so this, people would say, this has multiple names, but I guess this is what is called the forward difference, because you're adding an h instead of subtracting. So this would be delta sub h of f at x. Okay? So this is how you define it, exactly as this thing. And so what does this say? So what I was saying is that forget about the x. Delta sub h acts linearly on f. So delta sub h, f plus g, let's say c f plus g, is c times delta sub h applied to f plus delta sub h applied to g. That's what I mean by saying that this is a linear operator. And this is a finite difference operator. You see, and from this perspective, instead of putting the parentheses here, if you were to put it here, it says that this is basically the same thing as a derivative. Given this idea, you say, well, if the first derivative is like this, second derivative should be approximately this applied 2 times. That's what you say. And so, for instance, to get something like this, I'm going to first take delta h and then delta k. Or in this notation, delta h1 and then delta h2. Let me write it here. So what I just said is delta h f x is approximately f prime of x h. Or if you want to think about it like this, you can think of it as the directional derivative of f at x in the direction of h2. Right? This is the same thing. Maybe it makes more sense. And then you say, well, if this is the case, then certainly it should be the case that twice finite order difference should be the same thing as this, which really is also, in fact, a second order directional derivative, if you want. Now, the point in doing this is that, first of all, this, when you open it up, is exactly this lambda function. So you are really using this second order finite difference. I'm going to leave that to you to verify. This is equal to lambda h1, h2. And ultimately, you're trying to show that, well, you can differentiate first with respect to h2 and then with respect to h1, or the other way around, while you say that due to purely like algebraic reasons, when it comes to finite differences, you can switch to orders. You expand this, and it just turns out to be the same. And so first, the proof of this second order derivatives commuting is this. You first write this second order finite difference using this lambda function. You say that, oh, it's approximately this second derivative. And then you say, Well, because of the finite difference property, well, I can just switch the orders of the derivatives and then again take the limits, and that would correspond to the second order mixed derivative in the other direction. That's the idea. How do you substantiate it? Using mean value theorem, essentially. So mean value theorem you use to make sense of this, ultimately. And that's the proof. I'm not going to go any further than this, but this is how you prove it. You essentially apply mean value theorem twice. Okay? It's a very good exercise for you to take the argument described in the textbook, which is for functions going from R2 to R. But I'm telling you, essentially the same argument, when you the moment you sort of formulate it in this multivariable setting, works just as well. Okay? I wanted to prove this. It's a very nice argument, but we're out of time, and I want to move on. Okay. Any questions? Okay. So from now on, we can just assume this theorem. Certainly, I'm not going to ask you to prove this for a midterm or something, but at least you should be aware. And this is the intuition behind it. And in my opinion, the most sort of confusing part is this definition of this lambda function that you always start. That's what you use all the time. And likewise, you use the same thing to prove this and so on. All of them. They're all the same. Okay. So now let's talk about Taylor approximation. Let's let f to be a Cn function. Is that what I want? Let's say Ck. From m to n, so this is k times continuously differentiable. At each point in m, I would like to associate to f a Taylor polynomial. So let me let x in m also. Then the, what should I say? Order n Taylor polynomial of f at x is what you would expect. Of f at x is I'm going to write it like so. Capital T sub n of f semicolon x. Okay. Let's write it like so. If I were to feed to it any other point, x bar in m, this is going to be nothing but, well, in fact, let me write it like this. From m to f, take an x bar, send it to I from 0 to k, f differentiated I times, evaluated at x, the base point, divided by I factorial, applied to x bar minus x, I times. This is so that it is in analogy with the single variable case. But when I write it like this, I really mean, well, f differentiated I times at x is an I linear transformation. So it takes as input I vectors I'm saying feed this difference vector into all of the arguments. So that's what I mean. And in terms of this infinitesimal vector, you can also write it like so. Looks like the better. Taylor polynomial at x evaluated at x plus h is, well, here you're going to have only h. Oh, of course, I should say order k. Order k. K. Okay. So it's in full analogy with the single variable situation. Okay? It's just that this time, first derivative, second derivative, and so on, these are multilinear functions. And note that we defined what it means for a function to be a polynomial function in a multivariable setting. And we defined it so that whatever this expression was a polynomial. Okay? An important thing to look at is the difference between f and the Taylor polynomial, and that is what is called the remainder. Taylor remainder. This is the kth remainder, and this is nothing but f minus this polynomial. Okay. And so with these definitions, we can state the Taylor approximation theorem. Now, sometimes it is useful to use this notation. So x bar, a sufficiently close point to x, or x plus h notation. I personally tend to use this but you'll see this quite often also. So Taylor approximation theorem. There's a couple parts. Essentially, when you're trying to describe a Taylor approximation theorem, you want to say something like, oh, this Taylor polynomial is sort of the best fitting polynomial to f. That's what you should say first. And then you should say some sort of like bounds on this remainder, or if possible, you would like to give a formula for it. That's how any sort of Taylor approximation in any context works. Let's say, how did we write it? K, non-negative integer, and let's let f to be a function from m to n. Let's also let x to be a point in m. One. If f is ck, then in fact, this kth order Taylor polynomial of f at x is a unique polynomial that is tangent to f up to order k. That is to say, if f is ck, then is the unique polynomial function of degree at most k, possibly it's of lesser degree, of degree such that, well, I want to say that f is tangent to the Taylor polynomial up to higher order terms. This is the same thing as this at x plus h up to higher order terms. Here, the kth Taylor polynomial has terms up to order k, so higher order should mean anything faster than k. And of course, as h goes to 0. Okay. In fact, okay, let me finish writing the statement, and then I'll say a couple more words. Two, if you have more regularity, then you can say more things about this error term. So if f is ck plus 1, then in fact, this error term is big O. We hadn't discussed this yet, at least in this class. I'm going to tell you what this means. It's the big O of h to the k plus 1. So if you have more regularity, you get to say not only that this remainder it decays faster than h to the k does, but you say it decays at least as fast as h to the k plus 1 does. Okay. And finally, let's write it. Where do I want to write it? I'm not going to write it. There's also an integral formula, but let's not write it. There are many estimates and formulas for the remainder. So one of the benefits, of course, of using the Taylor approximation is that you get to pretend that any function, insofar as you can differentiate it, is a polynomial. And the difference, the remainder, is of lower order. So for many purposes, it's OK to just pretend that you have a polynomial function. So for instance, you can just, if you want to integrate f, instead of integrating f, which might be essentially impossible to integrate explicitly, but everyone can integrate polynomials, for instance. I should just say, what I was going to say was this. The way we sort of like developed all this machinery and theory actually allows us to basically write Taylor approximation we wrote for a single variable. And if you look at my notes from 30-10, or my lectures from 30-10, you're going to see pretty much the same statements. Of course, from the multivariable perspective, these polynomials and all that stuff mean more complicated things. That's the price you pay. But the same thing works. I should also say that ultimately, why is this a consequence of the mean value theorem? It's essentially really mean value theorem, but you induct on the number of differentiability, surprisingly enough. And that's, again, the same proof that you do in the single variable setting. Just to give you an idea, and also note that all the notation that we've been developing was so that this Taylor approximation comes out nice like this. And you may not think it's nice, but believe me, it's, compared to other things, it looks nice. So for instance, if k were 0, okay, c to the 0 means it's just a continuous function. Okay? 0th order Taylor polynomial is just a constant. Let me just do this. If it's continuous, t sub 0, this is a 0th order term. This is nothing but f of x. And what this says, first item says, is f of x plus h is nothing but f of x plus o of h to the 0. H to the 0 is just 1. And so for k equals 0, item 1 there just reduces to this. What does this mean? It means that the difference between these two, well, as h goes to 0, goes to 0. Okay? Because this means that the difference between these divided by whatever is inside the little o goes to 0 as h goes to 0. So this is nothing but the definition of continuity. And if I had, for instance, k equals 1, oh, let's do it like this. When k is 0, the second item says, if f is continuously differentiable, then f of x plus h is, well, it's the affine approximation, right? First order Taylor polynomial is f of x plus f prime of x at h. So that's the affine approximation that you computed, plus some higher order term. Yes. So f is in ck means f is continuous, and this. And then f is in ck plus 1 means f is continuously differentiable. Well, I guess I can just look at this. This is the affine approximation. If I use it over here, this would just give you the definition of differentiability. If I use it here, it's nothing but the mean value theorem. Right? Because by the mean value theorem, we have that f of x plus h is f of x plus some term times h, bounded. So this is what the mean value theorem says. And so that means that if you have k plus 1 differentiability, whatever, you can use mean value theorem k plus 1 times, and that would give you some estimates. Assembling them all together gives you Taylor approximation. That's the proof, okay? Idea of the proof. Mean value theorem plus induction. Again, I was hoping to prove this, but due to time constraints, I thought it's better to leave it as is and instead just look at an example where we compute some of these things. I would highly recommend, before thinking about this, going back to my 3210 videos and have a look at the discussion there. Once you understand how these things work, or at least how Taylor approximation works in one variable, it's pretty much straightforward how to generalize it to multivariable. Modulo that you understand how this multilinear algebra stuff works. But suffice it to say, at least for now, that multilinear algebra stuff is defined so that Taylor approximation works the way it does in single variable. Okay. There are other notations for these. So especially if M is a space of tuples or set of tuples, there is what is called the multi-index notation, which you're going to be dealing with a little bit, just the beginning of it. But then there's a bunch of like summations, and you would need to develop some more sort of like more factorials and stuff like that with vectors. And if you ever, go toward partial differential equations and stuff, that becomes more useful there. But since we're not doing any differential equations in this class, I thought it would be better to just stick to this matrix algebra flavored perspective. So that's that. Any questions or comments? Okay. So now, let's look at this example. Now, I should mention there are also converses of the Taylor approximation. Ultimately, you would want to say, oh, if I have a bunch of like multilinears that I can put together that depend continuously on the base point, insofar as some natural compatibility conditions are satisfied, they actually compile into a differentiable or CK function, whatever. It is also very useful, but we'll not discuss that further. So the example I want to give, where is this? Is here. It's going to be a polynomial function, x squared y, xy cubed. Let's let f go from R2 to R2. Takes a vector xy, and then what did I say? X squared y, xy cubed. The idea in this example is, well, I have 5 minutes, is to just compute some of these derivatives and so on. Of course, by now we know how to compute the first derivative. Right, so you just look at the first partials. So fixing an xy, f prime is going to be a 2 by 2 matrix because it goes from here to there. And on each row, I'm going to have one component. So this is going to be first row, and this is going to be the second row. On each column, I'm going to have one variable. First column is going to be the x variable. Second column is going to be the y variable. And x squared. And then y cubed. And then, what is it? 3x y squared. OK, this is the first derivative. How do you compute, for instance, the second derivative? Well, one of the things we can do is we can actually open this algebraically. Right? You would write f of x plus h and then y plus k. Plug them in. Because this function is an algebraic function, it's a function of algebraic origin, what is available in this particular situation is, well, I can just plug them in and just expand everything. And if I reorder or recombine things based on their orders in these infinitesimals h and k, well, I should be able to detect the first order derivative, second order derivative, and so on. That is to say, expanding this algebraically should be the same thing as the Taylor approximation. Because Taylor approximation says something, something, there's a unique polynomial. If I start with a polynomial, whatever I expand should be the Taylor approximation itself. Okay? So let's start doing this. I guess I'm going to take some time tomorrow as well. Here, and then y plus k. In the second entry, I have x plus h, y plus k cubed. Okay. Expand this out. This is the first entry, and then the second entry is, well, this cube, probably it's better to expand first. So you have this formula. Are we familiar with this? And you start with the cube and then 3 times whatever, 1, 3, 3, 1, and so on, 1, 4, 6, 4, 1, and so on. And then you expand these out. And then, because I'm running out of time, I'm not going to continue this. Maybe tomorrow we'll discuss this a little bit further. The point is that, let me just say, OK. I don't want to rush this. This is an important thing. I think it's going to make these statements that we discussed today a little bit more concrete. So I don't want to rush this. I'm going to take my time tomorrow. But that's it for this part of the class. Tomorrow, we're going to do this example in more detail. I'm going to tell you first order Taylor approximation and so on. And then we're going to switch to discussing the so-called inverse function theorem and its cousin, implicit function theorem. Thank you. OK, let's start. Good morning. Today, I would like to take my time discussing this function from R2 to R2. Perhaps show you in practice what it means for the second derivative to be symmetric, or mixed partials being mixed partials commuting, and also the Taylor approximation. And then we're going to switch over to the final topic of differential calculus that I think is very important, which is this implicit function theorem or inverse function theorem. So these are two statements that look rather distinct, but ultimately they are equivalent, implicit and inverse function theorems. We're going to get to that. But let's first discuss this. Now, first of all, remembering the Taylor approximation theorem, we have that any differentiable function is essentially a polynomial, or it can be written as a unique polynomial up to higher order terms. In particular, if I start with a function of so-called algebraic origin, this is kind of like a vague statement that is thrown around quite a bit. If I start with essentially an algebraic function, its Taylor approximation should coincide with the algebraic expansion. Okay, so that's going to be my starting point. And then when you think about what it means, what it could mean for this function to be of algebraic origin, well, you could say this is a polynomial function. How could you argue about this? Maybe I should ask you, how could I justify the statement that this function is a polynomial function?
We went over that thing with the transform, the way of thinking with polynomial functions and transforms, and observe that x squared is like the bilinear transform thing in R. And see that it's made among multiplications and x squareds and xy cubed.
Yeah, you could say that in this case, for instance, both of these components, so this component is in fact trilinear, right? You would feed to some function x, y, z, t, and then a, b, let's say. And then you're taking one of the coefficients from each of these vectors and multiplying them. This is what I mean. So if I were to call this guy f1, this is the first component. And f2, let's call it the second component, xy cubed. think of this as the output of some trilinear function where I plug in the same vector xy into all three components. And so I would write it like this. So let's try to come up with this trilinear function that would correspond to this. Okay? So I want a t, and let's denote it by, oh, let's not use, let's say s. So it's going to take three two-dimensional vectors, okay? Three vectors from here. And then the output, because I'm just looking at this component, is going to be a real number. Okay. So what do I want? And let's call this S1. Want S1, so our notation would be L sub 3 from R2 to R, such that F1 of xy is nothing but S1 of xy, xy, xy. Okay? Okay. Or if you want to abbreviate this, you would just write it as S1 applied to xy cubed, with the understanding that cubed really means I just plug in the same vector. Well, how could I come up with this S1? Well, I need to use this trilinearity property. And so even though this looks like this, I can simplify this a little bit. For instance, I could write like so. Okay? And instead of writing these as tuples, it's going to be easier to write column matrices as inputs. Now, if I were to fix the second and third entries, by definition of trilinearity, this S1 would be linear in this component, which means that I can pull out this x as a number, and then I would write it as S1, 1, 0, and so on. So 1, 0, xy, xy, plus y times S1, 0, 1, xy, xy. That's what it means for a function to be trilinear. If I were to fix these two entries, in the first entry it is linear. So I can distribute this linear decomposition. Does this make sense? OK. Right, just to be clear, here I use this idea that this first vector xy is a linear combination of 1, 0 and 0, 1 written like this. And then I distributed S1 over this linear combination. This is a number, so I can take them out. OK? Any questions about this? This is like, all this is as simple as this, really. You just apply linear algebra multiple times. But of course, there's nothing stopping me from applying the same reasoning to this entry and this entry. And see what happens. Let's do one more, for instance, here. Now, I'm going to have x squared, S1, 1, 0, 1, 0, xy. OK? And then xy, S1, 1, 0, 0, 1 this time. OK? Because this now contributes a y, and then xy. And then you would open up this one in the same way. Now I would have another xy with the entries switched. OK? And I would have a y squared. So xy, 0, 1, 1, 0. Okay, and then I have a y squared times s1, 0, 1, 0, 1, xy. Okay. I mean, while we're here, let's completely open everything. So applying the same reasoning to the final vector, I have how many sums now? How many summands? 8. X cubed. Just going to write it like this to abbreviate. So 1, 0, 1, 0, 0, 1. This is this part, plus x squared y, s1, 1, 0, 0, 1, 1, 0, plus xy squared, s1, 1, 0, 0, 1, 0, 1. This was this term. Now I need to open this up. This is the easy way to do this, OK? So you might be questioning. This is sort of the, how to say, systematic way of doing all this stuff. Oh. 1, 0, 0, 1. And finally, I have 2 of these, xy squared, s1, 0, 1, 0, 1, 1, 0. And finally, I have y cubed s1, 0, 1, 0, 1, 0, 1. OK? So I want to figure out s1 in such a way that this thing is equal to this function, which is this, x squared times y. And then when I look at this, I see x squared times y in how many ways? In how many places? Here, here, and here. OK? Because I'm not seeing any other components for this particular function, that means that the remaining so-called structure constants should be 0. What do I mean by structure constants here? Well, if I were to determine what this number is, what this number is, what this number is, and so on, I would be completely determinant S1. In other words, 8 numbers specifies S1 completely. That does make sense because it's an 8-dimensional space. You have 8 degrees of freedom. Once you fix 8 numbers, you fix one S1. So you want your S1 to be so that this number is 0. This you leave, this you leave, this 0. You leave this one. This is 0. This is 0. This is 0. And how are you going to deal with the remainder? Well, one thing you can do is there is some, this is like an underdetermined system if you want. You can distribute, you can choose whatever numbers you want here. But you could ask, oh, I want S1 to be symmetric. In other words, I want S1 to be so that it doesn't matter in which order I feed these vectors. You see, this is like 1, 0, 1, 0, 0, 1. And here I flipped the second and third entries. And here I flipped from here to there the first and the third entries. So you could say, I want S1, so each of these numbers to be 1/3. Then that would be a symmetric trilinear operator here that would indeed satisfy the equation that we wanted. It's 1/3. Then what is it? So this is 1/3. That's one way of doing this. Ultimately, this would show us that indeed the first component is a polynomial function. And I could essentially do the same argument with the second component. Now I would look at a 4 linear function because I know this is the product of 4 numbers, ultimately. So that would come from a 4 linear transformation. You would expand it out and so on and write down your thing. All this to say that this is of algebraic origin. That is to say, it's a polynomial function. Okay, this is sort of just like a review to understand how this multilinear stuff works in calculation. From a different point of view, you could safely say that if something looks like a polynomial, it is a polynomial. First entry is a polynomial of 2 variables. So is the second one. This should be a polynomial. Okay, this is the heuristic. But I'm doing this calculation to show that if you wanted to be more specific and more explicit, you can basically make a computer do this splitting for you. Okay? Yes?
Why is the second xy squared set to 0 and not? I'm just not
because
why you chose some to be 0 or not.
yeah, so ultimately I want this to be equal to f1 of x comma y. And when I look at f1 of x comma y, the only component I'm seeing is x squared y for arbitrary x and y. Which means that in this expansion, for instance, I shouldn't be seeing x cubed no matter what x is. The only way that can happen is if its coefficient is 0.
Well, if the other 3 are x squared y.
Yes.
Not x y squared.
Exactly.
I misread it.
Yes.
What does this look like if it's like affine, like you have like x squared y plus 1? How would it?
OK, so then what you would do is, so your colleague is asking, OK, in this case, I had one component, and it was clear that this was of order 3. But your colleague is asking, let's say that you have another some end here that is not of order 3. That plus 1 now would be an order 0 thing. But now you would go back to your thing, and you could say again, oh, this is still a polynomial of 2 variables. Or you could say, this part comes from a trilinear function, and this one comes from a 0 linear function. That is to say, a constant number. It's a number. Okay. So this is a trilinear, this is a 4-linear, and so on. In a sense, there are faster ways of writing this, and ultimately, if you've ever looked at physics stuff, there's things like Einstein notation and stuff. And ultimately, the reason why that is the case is that underneath a lot of modern geometry, and in particular things like general relativity, there's a bunch of multilinear transformations that sort of govern things. And so physicists, or people who need to do a lot of calculations with these things, they have more simplified ways of writing these things, more automated. Okay? But that is not our concern. So all you need for now is this. Any other questions? OK. So now let's try to use this idea and say, well, I'm going to plug in into f. Instead of x, y, I'm going to plug in x plus h, comma, y plus k, where hk is going to be a small perturbation. I'm going to expand it out using the algebraic nature of the function that I started with, and then try to sort of see the components of the Taylor approximation. Okay? And even before doing this, because I'm going to need the higher order derivatives as well, I'm going to be systematic, and I'm going to record the partials of both of the components the way that you're familiar with from Calc 3, let's say. So I'm going to do that here. Let's do that here, actually. And here's how I'm going to do it. I'm going to initiate 2 charts, OK? One chart is going to be for the first component, and then the second chart is going to be for the second component. If you look at the solutions that I wrote, I basically use the same method. And so the chart is going to be like this. I'm going to start from the bottom left corner. OK? I put the original function. Now I'm thinking of sort of an integer lattice here. And to the right of f1, I'm going to write its x partial, first x partial. What is the first x partial? This is 2xy. Okay, it goes like this. above f1, I'm going to write the y partial. And what is the y partial? Certainly it is x squared. Okay, so if I want to be a little bit more explicit, this is the x partial. So rightwards arrow is the x partial, and then upwards arrow is the y partial. Now, using the same idea, I'm going to go to the right or upwards using the x or y partials. Okay, so now I'm going to differentiate this using x. Now it's 2y, then it's 0. Okay, so first x partial, second x partial, third x partial is 0. Going up, this is just 0. Now here, I can go up this way or go sideways. Going up corresponds to taking the y partial of this. It's just 2x. But then I notice, oh, this is the same thing as starting from here and going rightwards. That corresponds to taking the x partial. Now this idea that x partial and y partial commutes in the chart looks like this. I can start here, do this, or do that. I always end up at the same function. Okay? Let's finish this graph. Go up, 2, go up, 0. And of course, once you have a 0, you're going to stay 0. In principle, if my function is sufficiently differentiable, you sort of populate this chart that way. Okay, it goes this way. And of course, if this is a constant, it's going to be a 0, and so on. Okay. Now, what is the rule here? The rule is, I'm imagining this chart to be in the integer points in the first quadrant in R2. And so I say, for instance, this is the 0, 0 entry. This is 1, 0 entry. This is 2, 0 entry, and so on. And then this would be 0, 1 entry. This would be 1, 1 entry, and so on. That is to say, at the alpha 1, alpha 2 entry, I'm seeing the alpha first x partial and alpha second y partial. So let me write that here. At alpha, which is alpha 1, alpha 2, this is a pair of non-negative integers. Put, how do I write it? Alpha 1 plus alpha second, alpha 1 plus alpha second partial of f, where you take x partial alpha 1 times, and then y partial alpha 2 times. That's the pattern. Okay. Why am I using this alpha here? This is basic to this multi-index notation. Instead of going into the weeds, I'm sort of trying to give you an idea as to how we can sort of imagine what all this like business is doing. Because some of you are going to be dealing with a lot of PDEs eventually. I want to prepare you. Any questions about this part? This is just like a recording. For the multilinear algebra stuff and Taylor approximation, we're going to have to sort of compile these in certain ways. So let's do the same thing with F2. Again, I start from the bottom left corner. So 0, 0, 0, 0 entry. And what is F2? It is xy cubed. If I go right, what do I get? Y cubed. If I go up here, what do I get? So y partial now. Going up is y partial.
Oh, I thought you meant from the y.
No, this one, this one.
Oh, 3y squared x.
Okay, so let's populate. That's a 0. And then this 6 xy, 6x, 0. And then this is, what is this? Okay, I could go this way, taking the x partial. I can go this way, taking the y partial. And this is 6y. Okay, matches either way. Go up, go sideways, doesn't matter. Then what else? So this is going to be 0, 0, 0, and so on. Okay? Now, why did we end up with essentially finite charts? That's because these are polynomials, and in finite time, or in infinitely many derivatives, I'm going to reach to 0. But you can imagine if I had started with something like cosine, I would have alternating terms, right? I would have, for instance, imagine having r cosine theta, r sine theta. R partials would be, so the chart for the r partial would be finite, but with the theta partial, you would have, what is it? It's like minus sine, and then minus cosine, and then sine, and so on. You would have these alternating things. Okay? So in a sense, the fact that this function that we start with is of algebraic origin is reflected in terms of the charts for partials, that these charts are finite. In finite time, you end up at zeros. Okay? So we're going to have to somehow compile all of these terms into this multilinear algebra stuff. But even before that, let's think about the orders of these terms. For F1, this term is the only order 0 term. Okay? Order 1 terms are the x partial or the y partial. This is the first order. Second order terms are this, this, and that. Third order terms, and so on. Okay? So you look at these off diagonals. And how could I say that in terms of the positions? Well, I could say this is, for instance, 1, 0, this is 0, 1. And if I were to add the entries, I would get 1. Here, this would be 2, 0, 1, 1, 0, 2. Add entries, I would get 2 again. So the order really is reflected by the so-called norm of alpha, which is the sum of the entries. So order k corresponds to alpha in norm, which represents alpha 1 plus alpha 2 being equal to k. Okay? Any questions so far? Why are we doing all this? Because ultimately, we would like to be able to, systematically keep track of these high-order derivatives without needing to worry about, oh, if I go this way or this way, it's the same thing, whatever. So now what I'm going to do is I'm going to start with the function, and I'm going to expand it algebraically. So let me remind you the function. Is it x squared y, x y cubed? I'm going to take, so xy is fixed. I'm going to take an infinitesimal, so to speak, vector, and I'm going to expand this guy. I had started doing this yesterday. Now I'm going to do it again. What is the point? Like I said, if I'm interpreting hk as my vector, or in other words, the infinitesimal, then if I were to expand this f, rearrange terms in terms of their orders in h and k, then that should give me the Taylor approximation. Now the point of Taylor approximation in general is that even if you didn't start with an algebraic function, insofar as you can differentiate the function that you started with, you can still come up with this expansion. That's what Taylor approximation is. So let's write this down. Y plus k, and then x plus h multiplied by y plus k cubed. Okay. Please, if you have the willpower, do this calculation with me. Keep me honest. Now, even though, of course, I'm saying xy is a point and hk is a vector, from the perspective of algebra, they are all just variables. So I can just expand things. So algebra doesn't really care about my interpretation of what these letters stand for. Okay, and then x plus h multiplied by y cubed plus 3y squared k plus 3y k squared plus k cubed. If you don't remember how to go from here to there, well, one thing you can do is you can split this into y plus k squared times y plus k, and ultimately it should add up being the same thing. Okay? But of course, if you know the binomial formula or whatever, it's good to use it here. Okay, so now I'm going to expand. And what do I have? X squared y plus x squared k plus 2x yh 2x hk plus yh squared plus h squared k. That's the first entry. Also note that as I was expanding this, I made sure that hk factors were at the end. Because ultimately, once I write this down, I'm going to split this pair of numbers in terms of their orders in hk. Okay? So now, because I'm thinking x and y to be fixed, I'm imagining x and y are constants, h and k are the variables. That's the first entry. The second entry looks like this. xy cubed plus 3xy squared k plus 3xy k squared plus x k cubed plus y cubed h plus 3y squared h k plus 3y h k squared plus h k cubed. Those of you who are following my calculations, does this match with what you guys are doing? OK. So now I want to split this sum into its orders. Not in terms of x and y, remember those are fixed, but in terms of h and k. OK, so let's do this. What are the 0th order terms? This is a 0th order term. First order, second order. OK, I have two of them. Second order, third order. Maybe I should write it actually. 0th order, first order, second order, third order, first order, second order, third order, fourth order. So let's write it like that. It says, so these are 0. It says 1, 1, 1. This one is 1. Second order. This one is second order. This one is second order. What's this? Third order. Then we have a fourth order term. Okay? So according to these orders, I'm going to now rewrite this polynomial. Let's write it here. You see, this is all like a bunch of grunt work, but that's all there is to it, ultimately. We've been developing all this machinery to essentially handle all this stuff in a systematic manner. But if you need, you can just open everything up and write them down. OK, so I continue from here. Maybe let's use colors, in fact, with the corresponding color scheme over there. So what is the 0th order term? xy cubed. It's my 0th order term. Remembering the Taylor approximation, 0th order term should be nothing but f of xy. That is indeed true. I duplicated f of xy as a 0th order term. Plus 1st order terms, these two. Oh, there's some, I think. Yeah, these ones. Let's write it out. Let me first write the one with h. Should be this one. And then here I have y cubed h, 3x y squared k. That's my 1st order term. What is the 2nd order terms? So I have 2nd order terms of 3 kinds. It could be h squared, hk, or hk or k squared. Plus. And let me write it in that order. H squared first, and then hk, and then k squared. So first entry, and then here I have 3y squared. Three xy k squared. Plus, now the blue terms. I have multiple blue terms in principle. I should start with h cubed and then h squared k and so on. But for instance, here I'm only seeing h squared k. And then hk squared. And then k cubed. Finally, we have the orange terms. In the first component, there is no 4th order term. In the second component, I have hk cubed. OK? Does this match with your calculations? OK. Going back to the charts, let's try to identify these. 0th order. Here is this, and here is this. 1st order, maybe I should have color coded these in the appropriate manner. So let me try to do that. Now, 1st order is green. So let's record this as well. This is red. 1st order term. 1st order term. 2nd order term. Y. here I have 2y, but let's not worry about it for now. There is some discrepancy, but it seems these coefficients, okay, boop, 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 they are related somehow. Somehow here I see y, here I see 2y, but then here I see 2x, and then it matches. There is some discrepancy. But never mind. Here again, you see, hk corresponds to the middle term. It's almost like h here corresponds to having an x partial, and k here corresponds to having a y partial. And here too, for instance, k squared corresponds to y partial twice, and it seems it's pretty much the right function. The coefficients are kind of messed up, but we'll get there. 0, and then you look at this, for instance, third order, 2x partial, and then 1y partial. It would correspond to 2, 1. It seems to match up. The numbers are messed up, but at the very least, the zeros are in the right place. Okay, there's a 0 over there too, that I can't reach. And here too, for instance, I have 3yx, which does match. Okay, and then finally, in this chart, I didn't have any fourth order terms. Okay, that's a 0. And then in this chart, there is a fourth order term, which is a 6. Again, the number doesn't match up, but at the very least, it's in the correct place. 1x partial, 3y partials. 1x partial, 3y partials. Okay? Any questions so far? Okay. So Taylor approximation says, by the so-called uniqueness part, that this is in fact the Taylor approximation of f of order 4. Okay? If you start with an order 4 polynomial, the fourth order Taylor approximation will be equal to itself, to the original function, on the nose. So there is no higher order error term. Okay. Any questions so far? Now we're going to try to sort of assemble these into the derivative, second derivative, and so on. So somehow, what is at stake is that we need to sort of compile this into one linear transformation of hk, this into a bilinear transformation of hk, this into a trilinear transformation of hk, and so on. Pull it down so that you can see. So what I'm going to write here is going to be the Taylor approximation again. But this time, instead of using the algebraic expansion, which I had available due to the algebraic nature of the function, I'm just going to use the calculus way of doing the same thing, which is just writing the derivatives. And by matching the terms, we're going to figure out what the derivatives should look like. Okay. 0th order term. Okay, let's call it code also. So we started with red. 0th order term. Plus, first order term is green. Okay. Plus second order term, that is yellow. except that, remember from Taylor, there's a correction factor here. You have to divide it by 2 factorial. Okay. Now, what does this mean? This means that if you want, maybe it's going to look better, 1 over 2 times this. And then the next term is blue. That's a 3rd order term. F triple prime xy. So this is going to be a trilinear transformation. I'm going to feed hk 3 times into this. And that I'm going to just denote by hk cubed. And again, there's a correction factor, which is 1 over 3 factorial. That is 1 over 6. Plus, the final term is 4th order. And again, the correction factor here is going to be 1 over 4 factorial. That corresponds to multiplying 6 by 4. That is 24. OK? Now, we started with this algebraic function. On the one hand, we expanded it using merely algebra. On the other hand, we said algebraic functions should be differentiable, so I should be able to apply Taylor. Then we said, by the Taylor approximation theorem, this expansion should be unique, insofar as I expand it into multilinears, which means that the terms here should correspond to the terms there, where you match red with red, green with green, and so on. OK? Any questions about this so far? Well, we already learned that this I can think of as a linear transformation of hk. And when you open it up, it basically turns into this, right? Let me just write that down. So this should match with this, but I can think of this as a 2 by 2 matrix applied to hk, like this, right? So and then here I have x squared, y cubed, 3xy squared. And then I could say, oh, the linear transformation that is, or the matrix that is supposed to represent f prime of xy should be this matrix. Okay. Now the problem, for instance, is to likewise match this with this. And even before that, perhaps I should mention, well, if you look at the charts, the first order terms went there, and then these first order terms went into the second row. Okay? We said in the derivative, in the matrix that corresponds to the derivative, each row corresponds to 1 component, which means that this corresponds to these first partials, and this corresponds to the second partials, rather, the first partials of this. Now, how do you write, likewise, f double prime xy using linear algebra? Well, the idea is this, okay? And some of you some of you know this. If I can represent a linear transformation as a matrix multiplication from the left, well, if I want bilinear, what I could ask for is, well, I could write it like so. This term should really be like this. Use 1 matrix multiplication from the left and one matrix multiplication from the right. That is to say, take one of these inputs, put it to the right, take the other one to the left using the transpose, so that the matrix algebra works. Okay. Of course, when you do this multiplication, it's going to give you a number, which means that this is only for the first component. You're going to have 1 for the second component as well. Okay. So this is the first component. This is the second component. When you look at this matrix algebra, it has to match with, so it has to give you a number. So this is going to give you the first component. This is going to give you the second component. And because I'm running out of time, I'm going to leave it to you to verify, to figure out how to compute these 4 entries so that you get this and that. Right? So what you can say is put arbitrary variables, a, b, c, d, multiply this. It's going to give you an expression that depends on a, b, c, and d, then match the terms. Again, I'm going to leave it to you to verify, to figure out what the pattern is. How do you go from these charts into these coefficients? Okay. This is underdetermined, but what you can say is you can use this idea that mixed partials commute, and instead of looking at an arbitrary matrix, you can just solve for a symmetric matrix. Then this is a unique solution. Okay. Okay, that's it. I wanted to discuss more, but we're out of time. We're done with this. Tomorrow we're going to study inverse function theorem and implicit function theorem. Thank you. Okay, let's start. Good morning. So today we're going to start discussing implicit function theorem and inverse function theorem. Remember, I mentioned how these two statements, even though on the outset they look different, they are pretty much the same idea. In fact, one implies the other one. Before that, though, I wanted to mention a couple more things as to the scope of the stuff that we discussed so far. And perhaps even before that, I should say one more word about this example that we were discussing about Taylor approximation. At the end of last class, one of your colleagues asked, okay, so we could do the first order approximation, second order approximation in terms of matrices. How do you do the third order approximation? Right, so because we said if you want first order, then I can just think of a matrix and I'll feed the infinitesimal matrix column matrix next to it like this. That would be a linear transformation. For second order, again, I could take a linear transformation and I could feed one vector this way and the other vector this way, essentially, to get a bilinear guy, right? Because this is linear, this is also linear, so this is bilinear now. How do you get a third order thing in terms of a matrix? Well, it's kind of finicky. So if you read my solution, so in the selected solutions, I kind of did something that would correspond to a matrix representation like this for the third order term, but it gets kind of janky. Starting from the second order, you start feeling sort of the limitations of matrix algebra. And there are different notations for third order and higher. They become more sort of like circuit-like, let's say. So there's a bunch of like notation, Penrose notation, and so on. Penrose, tensor notation, etc. And so you sort of write down certain circuitry or networks, and to these like so-called tensors, multilinear functions, you associate certain sort of like circuits, and that sort of like allows you to, and it has certain sort of like rules. For us, we're not going to get there, but it is available. Okay, so third order and higher, it's still very important. There are certain methods to do sort of like calculations, just like you can do matrix algebra in higher order multilinear functions as well. You can do things, but we're not going to get there. Still, I think it's good to try to get away with, computing multilinear functions using matrix algebra. So in math, in sciences, we have all of these very compressed ways of doing things, matrix algebra being one of them, for instance. And I feel like one of the best ways to appreciate these more compressed notation is to stick to the standard way of doing things, or the conventional way, or the way that you know how to do, and try to push the notation further and further. And then you eventually start seeing, oh, my method or my notation starts to sort of burst at the seams. And then you say, either I'm not going to think about third order things, or I'm going to have to come up with some new notation. And this is how people come up with new ways of writing things, OK? OK. So the first example I would like to give is about what you could say least action principle. So this is a general principle in mathematical physics, or physics in general, which is this idea that in nature, nature decides among all possible ways of doing something, the way that minimizes the action, so to speak. So this is like a technical term coming from physics. An example is something like this, OK? Let's say that I have here an open set in my norm space E. OK? Something like this. And let's say that I fix 2 points in my open set. Let's say this and this. I can consider the collection of all continuous paths from this to this. OK? That's a metric space under the C0 metric. Paths from x1 to x2, but I'm just restricting my paths to be completed within M. So I'm not allowed to leave the set. So in M. OK? So in this set, each element is one path. OK? Like this. Maybe there's one that goes like this, and so on. What you could ask in this case, you could try to optimize the length. We know how to associate to a path in a metric space a number, possibly infinite, which is called the length, right? Length takes a path and sends it to an extended non-negative number, as you discussed as you computed in a previous problem set. And you could say, well, what are the paths that actually minimize this function? OK? And so we didn't discuss this, and I'm not going to discuss it any further. But you could say, based on our understanding of multivariable calculus, well, you could try to differentiate this length, set it equal to 0, so that you can find the critical points, so the critical paths. And critical paths should be basically the length minimizers. OK? And so you would say, if gamma is a path, let's say that gamma bar is a small perturbation. OK? So gamma bar is gamma plus h. Now, these are supposed to be functions, though. What does this mean? This means that h is a small function, small in the C0 norm. So h of t in norm, where the sup varies from, let's say, where t varies from 0 to 1. You want this to be bounded by some epsilon. So you see, this would be sort of your initial, this would be your position for the length function. This would be your small perturbation. And you could try to relate the length of this to the length of this. So you would open this up. There's a soup over something, right? There's plus, if you can come up with a linear operator that takes as an input this small perturbation and gives you back a number, that's basically the derivative up to higher orders. And so at the very least, insofar as x1 and x2 are close enough, you should expect that, for instance, minimizers of this length function should be straight lines. But of course, if I were to give you the 2 points so that x1 and x2 are, well, they cannot be connected by a straight path, then things get more complicated, you see. If I were to give you something like this, you would try to minimize the length of this path like this. The way I wrote it like this, you can't actually solve it. It's, I tried. You can't actually sort of relate this to this. But if you assume just a little bit more, you can do things like this. And people do it. And this is sort of the starting point of calculus of variations. Okay? And if you ever take a PDE class, this, once you sort of open this up, turns into a PDE, which is called the Euler-Lagrange equations. Okay, you know. The point of this is that maybe whatever process that you're looking into is so that what is being minimized is not length, but it's something else. So in general, instead of having this length, you have what is called a Lagrangian. And you're trying to minimize that Lagrangian. Okay? So this is a very important thing to be able to do. All I'm trying to say here is that even though I'm not developing this any further, what you learned so far, verbatim, is going to apply to this context. Okay? This, for instance, is an open subset in the norm space of all C0 paths from x1 to x2 without the restriction in M, and so on. So everything is going to apply verbatim. Now, how to do this, right? How to expand length of the small perturbation of the path up to first order like this. Now that's something that you're going to have to deal with separately. Okay? That has nothing to do with differentiability, whatever. In this class, we were just focusing on the general principles. Okay. Another example I would like to give is, because I know some of you are interested in AI, language models. There's something called differentiable programming. The idea being that in this paradigm, you have computer programs, each parameterized by some open subset of some norm space. And you have a certain objective function. Let's say that you have an architecture for a large language model. There are multiple architectures. Let's say one of them is what is called feed-forward. You have the input, and then you have like multi-layers. You sort of like keep sort of like pushing the input you have. In any event, you have a subset of some norm space where each point in this open subset represents one specific set of parameters. So imagine, for instance, they say, oh, with ChatGPT, they have 5 billion parameters. That means that each instantiation of ChatGPT is one point in sort of like 5 billion dimensional space. And you have an idea as to what you want the ultimate program to be able to do. Detecting cat, differentiating cat from dog or whatever. And so there's a function. Again, you're trying to optimize. And so you differentiate the program based with respect to the parameters. But now, because even though ultimately your variables are finitely many, there are so many that you cannot actually just compute everything. These are complicated things. And so they have all of these ideas like autodiff, automatic differentiation, backpropagation, blah, blah, blah. There's a bunch of algorithms that allow you to actually efficiently differentiate these programs. Okay? But the underlying sort of general principle is what we've been discussing so far. Going one step further, from a mathematical or logical point of view, programs are the same things as, approximately the same things as proofs. So you can also think about differentiable proofs. I'm not sure if anyone did anything with this. Maybe in 10 years I'll do something. But what could that mean? Well, if you imagine sort of like an epsilon delta proof, typically we choose 5 epsilons and 7 deltas, and they all depend on each other somehow. And some of these choices work in the proof, some of them don't. But you could imagine differentiating the proof itself. So imagine the proof as a mathematical object in and of itself. You can imagine how, or perhaps you could differentiate the proof with respect to the variables that you were using, and then look at the critical points. You see, from a certain perspective, one of the things we did, for instance, in the context of mean value theorem, we were trying to establish an inequality like this. And instead of this, we added an arbitrary parameter. And then somehow, I'm sort of being super vague here, it kind of sounds like what we were trying to get is sort of a critical point of this proof that depends on epsilon. Okay? I'm saying these things so that you sort of like get creative. I'll let you cook. So this is the beginning point. This is the starting point. Of course, in this case of program proofs, it's like how are you even going to come up with the norm space that is the space of all proofs, whatever. Okay? Things get complicated. I'm not saying we can just verbatim do this, but food for thought. Ultimately, one of the points of math or learning these more advanced classes is to be able to imagine how things could progress. Okay. Any comments or questions about this? Okay. Back to reality. Inverse function theorem and implicit function theorem. By the way, even though I didn't see differentiable proofs yet, there is sort of like some research toward it, because right now people are trying to automate theorem proving using sort of AI systems and stuff, which I think is very fascinating, but I don't quite understand what these guys are doing really. Anyway, maybe some of you will eventually. Okay. Back to reality. I want to discuss 2 problems and theorems. One of them is the inverse function problem, and the other one is the implicit function problem. Okay. So problem 1 is the inverse function problem. I'm going to be vague. Not going to worry too much about the assumptions and so on, because I just want to give you an idea as to what we're trying to do with what ultimately ends up as theorems. What you're doing is this. I'm going to write it like so. You're given a function, okay, 1 input, 1 output, and the fact that f takes the input you chose to the output you chose, and sends it to the output you chose. let's write it like this. Such that, don't worry about what these are. F is a function, x is an input, y is an output. I want to be sort of like flexible. What I want is to essentially start with this and solve for x. Solve f of x bar equals y bar for x bar, where x bar is a small perturbation of the point you were given, input you're given, and y bar is a small perturbation of the output you were given. Where x bar is x plus h, y bar is y plus k, h and k small. Okay, so what do I mean when I say solve this? That is to say, this equation, or nearby this equality. Solve the same equation for nearby points. And what do I mean when I say solve for x bar? I want x bar to be a function of y bar. So I want to sort of revert the functional relationship. When I write it like this is the independent variable, this is dependent variable. I say I would like to be able to switch their roles and think of this as the dependent variable and this as the independent variable. Does this make sense so far? What do I really want? Then let's try to be a little bit more explicit. Well, I want a function, let's call it lowercase phi, such that, let's write it like this. F of phi of y bar equals phi of x bar, equals x bar. So this means now I get to think of x bar as a function of y bar. I want this to satisfy this still. So x, y, and y bar related this way, I want them to satisfy the thing that I was trying to solve. So f of phi of y bar, I want to be equal to this. And I want this to be satisfied on the nose. That is to say, I want phi of y to be equal to x. I want one phi like this, but really I want a unique one, okay, if possible. Does this make sense? Okay. Now, based on this, assuming that we have, calculus, all that stuff, let's try to come up with an infinitesimal necessary condition. So that means that I'm going to think f is differentiable sufficiently many. I don't care at this stage. Phi is differentiable sufficiently many, such that I'm saying, let's say that I have such a phi, and I have calculus available, so that I can, at least in the context of calculus, come up with a necessary condition. For now, we're just looking at this from an intuitive point of view. Later, I think, toward the end of this class, I'm going to state the associated theorem more precisely. Where do I want to write it? Let's write it here, because there I want to write the implicit function problem. Okay. So necessary condition Well, let's think about this. Well, I have here this equation satisfied. So again, in my notation, in the stage, x and y are fixed, but x bar and y bar are arbitrarily small perturbations that are not fixed. Okay, that's how I'm imagining this. What I can do is I can take this equation and differentiate. By way of chain rule, I can differentiate this. And so I'm going to try to come up with a necessary condition. That is to say, if such a phi exists, then this has to be satisfied. Right? That would be a necessary condition. I'm going to try to come up with a necessary condition by differentiating. And so if I were to differentiate this, by the chain rule, I have f prime evaluated at phi of y, in fact. I can just focus on derivatives at this input and output, multiplied by phi prime at y. And on the right-hand side, well, this is just the identity function applied to the input, now y bar, which means that this is just going to be identity. Well, if this is the case, I should be able to take this to the other side by taking the inverse, in which case phi bar would be nothing but phi prime would be nothing but f prime inverse. So a necessary condition would be that this thing, which is a linear operator, is invertible. So that means that I want this to be invertible. But of course, when you think about it, phi of y is nothing but x. So I can write this as this. Well, maybe it was better to leave it like that, actually. And so a necessary condition is that this one is invertible. Is invertible with bounded linear inverse, right? Oh, let's just leave it like this for now. Invertible. That's my necessary condition. Any comments or questions so far? Inverse function theorem says the necessary condition is also sufficient. Meaning, insofar as we have calculus available, we're going to get to the details later, if f prime at this input you were given is an invertible bounded linear operator, then you can solve this. You can solve the problem that you have. Insofar, and that's going to be the assumption that we're going to need, insofar as the underlying spaces are complete in the sense of metric spaces. So I'm just going to write here, provided completeness. Completeness in the sense that whatever space underneath are involved, I want Cauchy sequences in those spaces to converge. Okay. And this is the inverse function theorem, at least heuristically. Okay. Any questions about this? So this is problem one. Inverse function theorem, inverse function problem, inverse function theorem. Second problem is the implicit function theorem. this time I'm given an f, x, y, and z. And I want these to be related so that f of xy equals z. Okay. Again, don't worry about the types of these things. We're going to make it more rigorous later. What I want this time is that I want to fix the output z, and assuming that the output is fixed, I want to think of y as a function of x. So I want to say, oh, this equation defines y as a function of x, really, implicitly, right? Implicit function. So solve f of x bar, y bar equals z for y bar. So you see, I'm perturbing x, I'm perturbing y, I'm fixing the output. So my perturbations should be so that the level set is fixed. So the height is fixed. So for y bar, and again, where x bar is a small perturbation of x, y bar is a small perturbation of y. So these are small. And again, writing it out in terms of functions, what I would really want is this. I want a function phi. I want it to be, if possible, unique, such that, how to write this? So I want y to be a function of x. So y bar is going to be a function of x bar. What else do I need? Well, I want this to be satisfied. And I want, when I plug in, instead of y bar, phi of x bar, I want this to be satisfied. Okay. This would what it would mean to solve this expression for the second variable. So that I would say that phi is, or y is an implicit function of x. Any questions about this? And like I did over there, let's try to come up with a necessary condition, assuming calculus. So what am I going to do? This time I'm going to differentiate this guy. How do I differentiate it? Well, you can do implicit differentiation, whatever. Technically, we just use the chain rule, of course. So I start here. Now note that the output is constant. So when I differentiate this expression, right-hand side is going to be 0. But the point is, f prime, because it has two variables, it's going to have the d1f, right? So the horizontal partial or the x partial, and then the d2f, which I'm going to have to adjust using this. Imagine these are all just numbers and stuff. So the chain rule, we developed everything so that what you're familiar with from Calc 3 basically applies. And so, and again, I'm just going to look at the derivative at the initial point, xy. Okay, so the derivative of the second one times the derivative of the thing inside equals 0. Okay? So now, again, I'm going to solve for this. So I can send this to the other side as a minus the operator. And then that would mean that I need this to be invertible. Okay? Minus d2f(x) px inverse d1f(x) px. And so that means that just like in this situation, in order for me to be able to write it like so, well, I would need that this guy is invertible. So I need the vertical partial to be invertible. And instead of writing it like this, because I'm expecting phi of x to be y, I can just say d2f at xy, invertible. Implicit function theorem says necessary condition is also sufficient, provided completeness. Necessary condition is also sufficient, again provided completeness. Okay. Any questions about either one of these? So let's think about examples of these. So for instance, I can think of something like this. Let's imagine these are all just numbers and stuff. Then this should be familiar to you. And so f prime of x being invertible in 1D just means that f prime of x, which is in 1D just a number, is not 0, right? That means that if at a point x, the graph of f is not horizontal, right? So if it's not like this, maybe it's like this, then you get to invert your function f. Because when you really think about it, this equation means that phi is an inverse for f. That's why this is called the inverse function theorem. And an example for this would be something like, oh, if I were to start with x squared plus y squared equals r squared for r, let's say, a positive or non-negative number. Well, this is, of course, certainly the equation of a circle at the origin, centered at the origin with radius r, right? And we know how to solve for y. You would say, oh, y is, what is it? R squared minus x squared in square root plus or minus. But this does make sense insofar as, so what is the y partial here? 2x, insofar as y is not 0. Because when y is 0, you're here, and near this point, you cannot write y is a function of x, right? It fails the, what is it, vertical line test. Insofar as y is not equal to 0, then you get to write y is a function of x, either like this or like this. Comments? Questions? So these are, again, very important things coming from differential calculus. And I'm telling you that they work in finite dimensional spaces, infinite dimensional spaces, insofar as you have the Banach space property. They work. It's fine. Now I'm debating as to whether or not I'm going to give detailed proofs of these, because we need something, piece of machinery. But at the very least, let me say this. Okay? Those of you who are perhaps comfortable with differential equations would recognize that this is a differential equation. Never mind that this prime is it could be sort of like a bizarre derivative. First prime is, OK, so this is the right-hand side. OK, so the right-hand side still depends on the function, though. That's fine. That's something you can handle in differential equations. And you have an initial condition. So these two boxes really give you an initial value problem. And those of you who are familiar or comfortable with differential equations know that whenever you have a so-called initial value problem, there's a unique solution. Okay? Just like I want here a unique solution, within the world of differential equations too, you have unique solutions once you have a differential equation like this and an initial condition. Now the problem is, within the context of differential equations, of course, well, you would like to think of this as an ordinary differential equation. So you would want your derivative to be one variable. So this is sort of like a generalized initial value problem. Still, you can prove it. You can solve it. So let me say this is just an IVP. OK? And likewise, this, together with this, again, is an initial value problem. So at least as a heuristic, those of you who are familiar with this idea that when you have sufficient regularity, whatever, your initial value problems have unique solutions, should expect that these should be true also. Now the idea is that ultimately the idea works, this heuristic is accurate, and the piece of machinery that we're going to need to prove this and this is also the piece of machinery you actually use to prove existence and uniqueness for initial value problems. And this machinery is what is called the Banach Contraction Principle. OK? So let me write that here. BCP implies existence and uniqueness. It implies inverse function theorem. It implies implicit function theorem. It implies many things, OK? In any type of math, the moment you see completeness assumptions, you may not perhaps see it explicitly, but if there's a completeness underneath, and if the outcome is there exists a unique, 99.9% of the time, underneath, there's this Banach Contraction Principle. OK? So it turns out that this is only this is something that is for abstract metric spaces. It's a very general principle, and that's why it has so many uses. So we might prove this, or maybe I'll give you the complete proof of either one of these, black boxing this. We'll see. I'm still debating. what I do want to show in the remaining 5 minutes is that, in fact, these two problems are equivalent. So really, if you can solve one, you can solve the other one, and vice versa. Okay. So in the textbook, for instance, they prove this, and then they prove implicit function theorem using inverse function theorem. I find it slightly more pleasant to prove first this, and then go back to this. And in the textbook too, they use not this Banach Contraction Principle. They use a slightly different method. It turns out that these theorems have like 5 different proofs. They're all like very different in style. The proof in the textbook doesn't quite, well, okay, you can still generalize the proof in the textbook to arbitrary dimensions, but it takes more sort of work, and we would need more sort of technical statements. But somehow, if we just take this, everything works out beautifully. So this is the method that I'm going to discuss. So let's verify that this, if you can solve this, you can solve this, and vice versa. Before that, I should ask, are there any questions about any of these? Okay. There are many sort of solutions, really. There are many inverse function theorems, implicit function theorems, within calculus, outside calculus. Depends on what you get to assume based on the situation. Because when you have a functional relationship like this, it is a very common thing to want to be able to do, to revert the relationship. And again, implicit equations like this are very common, and you would like to be able to solve x for y or y for x. So where do I want to write it? I want to keep this, so let me delete this. So let's start with the easier side. Suppose you can solve the implicit function problem. Okay? Don't worry about the theorem itself. Let's say that you're given this problem and you get to solve it using calculus. My claim is that you get to solve the inverse function problem also. So 2 implies 1. What does this mean? It means that I'm going to start with what I'm given, rewrite things in such a way that is compatible with this problem, solve, assume the solution there that is guaranteed based on this assumption that I get to solve implicit function problem, and then reinterpret the solution that I obtain here in terms of the paradigm here. Okay, that's what I mean when I say 2 implies 1. And so if I'm trying to solve f of x bar equals y bar, well, what I can do is I can take y bar to the other side and think of f of x bar minus y bar to be a function of x and y. So let me denote that by capital F. Okay? So now I'm going to try to use the implicit function problem paradigm for this capital F. And so what am I trying to do then? I'm trying to solve, well, I'm given that capital F at xy is equal to 0. And I'm trying to solve for capital F x bar, y bar equals 0 also. So have for, well, I'm trying to solve it for x really. So for x bar. Okay, so in this situation, z would be 0. Okay. We also have this necessary assumption for the inverse function theorem, which is that lowercase f prime at x is invertible. Oh, I'm out of time, I guess. OK, we're going to continue talking about this on Friday. Thank you. Apologies for not stopping on time. I'll see you on Friday. OK. Good morning. Let's start. So today, I would like to keep discussing these two important parts of theorems of differential calculus. One of them is inverse function theorem, and the other one is the implicit function theorem. On Wednesday, we were talking about certain types of problems these theorems were supposed to answer. So inverse function problem and implicit function problem. I'm going to go over these again. Then I'm going to state these theorems more accurately. And then we'll go from there. I would like to discuss how, if you can solve this problem, you can solve this, and vice versa. So even though these problems look kind of different, they're actually the same problem. So you can convert one problem into the other one, which means that the proof of one theorem implies the proof of the other theorem also. And then instead of perhaps giving a complete proof, I'm going to discuss items or elements of the proof. And I debated this, if I want to sort of move on, if we end up not finishing this. And I thought, still, I think I'm happy to sacrifice some more of integral calculus next week. So we'll see. Ultimately, the reason is, well, I'll tell you the reason later. Somehow, there is also more sort of general integration theories, or we could discuss integration or integral calculus in much more broader context. The flavor really changes when you switch over from Riemann integration to something that is more sort of applicable in more general situations, Lebesgue integration, Bochner integration, whatever. But then if you're not going to be switching our paradigm of integration, that is to say, if we're going to still stick to Riemann integration and multivariable calculus, then the theory is kind of janky. And those of you who are going to need to do integration in much more broader contexts, you're going to learn better integration theories. So I'm going to keep integral theories, integral calculus to a minimum. That's sort of my understanding, my worldview on this. But we'll get there. Another thing is that we have next week on Friday scheduled our second midterm. So as usual, you should expect an email from me by the end of today telling you what you should expect, all that stuff. If not today, maybe tomorrow or something. And there's a problem set that we need to grade as well. Hopefully you'll get your grades on problem set 6. That was due last week, I think. Hopefully soon. And just as before, we're going to try to grade the problem set that is due today before next Thursday, let's say, so that you'll have some time. Any questions? OK. So let's start. Let's remember first this inverse function problem. What was the situation? We were given a function f, an input x, and output y. I don't really care about the types at this point. All I care about is that these are supposed to be within the world of differential calculus. While there are more, so you can interpret inverse function theorem or inverse function problem in much more general settings, we're just looking at the sort of vanilla differential calculus version of it. And what we would like to do is, well, we would like to perturb the given input x to some x bar, and the given output y to some y bar. And near the data that we're given, we would like to essentially extrapolate the equation. Okay? And really, after this extrapolation, we would like a specific formula for x, or x bar, in terms of y bar. That is to say, I want to set up this f of x bar equals y bar near this data I was given, and I want to solve for x bar. In other words, you can think of it as trying to find a local inverse for f. And when you sort of write it out, it really means a function phi that fits the initial data. Okay? And when I feed into f this phi, so this you can imagine as solving for x bar. Well, when I feed it, I get back y bar. That's what it means from a sort of more actionable point of view, let's say, to solve this equation for x bar. Any questions about this? This is an important topic. The problem, understanding the problem, one could argue, is even more important than understanding the theorem. Okay? Once you understand the problem, the theorem essentially is going to sort of prove itself, state itself and prove itself, perhaps. It's important to understand the problem, though. Okay? And then we did some calculations. What did we do? We said, oh, let's assume that all of the functions are differentiable, calculus, whatever, all that stuff. Let me just differentiate this equation. When we differentiated this, we realized that a necessary condition for such a phi to exist is that f prime, the first derivative at x, which is a bounded linear operator, or it's supposed to be ultimately, is invertible. If x and y were numbers, this would just mean that f prime is not 0 at x. Okay? In more general settings, that means that I want this to be a bounded linear operator that is invertible. I'm going to write what this means more precisely. And then we also discussed how, well, you can think of all this in terms of a sort of generalized initial value problem. You would set up something like this. So this is your, so to speak, ODE. Right? So this is your left-hand side. Phi is your unknown. On the right-hand side, you have something, some force function. And you also have an initial condition. That's your initial condition. This is your ODE. And you want to solve this equation in a unique fashion. This was sort of like a summary of what we discussed, or part of what we discussed last time. Any questions about this? OK, let's switch over to the implicit function theorem. Now I'm given 4 things: a function f, 2 inputs x and y. Maybe I should have written it as x1, x2, but never mind. X and y, let's imagine as inputs. Z is an output, so z is a height. Okay. This time, what I want to do is I want to fix the output, so I want to fix the height, and I want to vary the input variables. So you vary x into x plus h, x bar, and y into y bar. Okay? And once you have this, so to speak, level set, right? So because imagine f is sort of the height function, you're fixing a certain height. You say, I'm just going to look at the subset that corresponds to the height z. Imagine this is sort of like a, I don't know, map or whatever. What you want to do is you want to only focus on this level set, okay, where the level is always z. I'm not perturbing the output, but I'm allowing the perturbation in the inputs. So I'm just moving along this level set, okay? So when I write it like this, that's really what that means. I'm allowing x bar to be perturbed, y bar to be perturbed, subject to the constraint that under these perturbations, I'm still in the same level set. So for instance, if x, y were at this point, I'm not allowing perturbation in this direction. I'm only allowing perturbation along this level set. Okay, that's why there's no z bar here. And now that I have this, I want to solve this equation now in terms of y bar. That is to say, I want to think of y bar as a function implicitly defined of x bar. That is to say, let's imagine this is x, this is y. And let's say that this level set is the one that corresponds to height equals z. Okay. Right, this is not the graph of a function because I'm just drawing the input space here. So this is f of x bar, y bar equals z. And I'm given one point x, y here, let's say here. That's fixed. And so instead of trying to write y as a function of x for all points in this level set, I'm just localizing and I'm just restricting my scope. And I'm saying, if I have here this point, can I write at least a little piece of it, a little piece of the level set as a function? Right? So if I were to just think of this loop, it's not a function of y, right, because of the vertical line test. But locally, nearby this point, it is a function of y. OK, that's the point. And so there is a function, and if possible, I would want it to be unique. I want the function to match the initial data. And when I feed, instead of y bar, if I were to feed phi of x bar next to x bar, I want this to be in the same level set. That's what I'm saying. That's what it means to solve this equation for y bar. Any questions about this? Yes?
It seems related to Lagrange multipliers.
Yes, it is related. That's why I let go of Lagrange multipliers. Yes? Yes, you can think of this as, so from a different perspective, this is a problem of constrained optimization, or it is related. Good point. Any other questions? Okay. Yeah, so from perhaps like an economics point of view, let's say f is a cost function, and x and y are two of your, I don't know, resources. Or maybe the things that you require to manage a certain thing, and z is your budget. So you want to say, well, fixing the budget, what can I do with varying the inputs? That's sort of the starting point. We're not really optimizing here, technically anything, but it's along the same lines. Very good. And then we did some calculations. What did we do? We took this equation last time, differentiated it, okay? And we saw that a necessary condition for phi to exist is that the second partial of f at the initial point is invertible. And again, we could write it in terms of initial value problem form, initial value problems. Again, I have a differential equation here, ordinary differential equation, so to speak, and an initial condition. If you believe in a lot of things that they tell you in differential equations, this you should expect has a unique solution. Okay? Any questions about either one of these? OK. And let's go back now. What does the inverse function theorem say? Assuming completeness of the underlying spaces, the necessary condition is also sufficient. What does the implicit function theorem say? Assuming completeness of the underlying spaces, the necessary condition is also sufficient. Okay? That's sort of the fast way of thinking about this. But obviously, we need to, given that this is sort of like a proof-based class, we need to make sure what that actually means. OK. Another thing is that I want to take my time today and verify that indeed these two problems are the same problem, really. You can take this problem, turn it into this problem, and vice versa. before doing that, let me state the precise versions of these or one precise version of each of these. Then go back to the problems, see how you can convert one to the other one. So inverse function theorem goes like this. As usual, we have the standing assumption. M is an open subset in some norm space E, and N is an open subset in some norm space F. Let me write it here. Opens in norms, normids. OK. Let's see. I want to start with a rigorous statement of the inverse function theorem. Let's think. OK, let's write it like so. Let k be a positive integer or infinity. This is going to be my regularity. I'm going to want f to be ck, c1, so once continuously differentiable, c2, whatever, maybe infinitely differentiable. Ultimately, what I'm going to ask is that this phi function 2 is of the same regularity. So if I start with c5, I want phi to be c5, and so on. And let me let x to be in M. And let's let f to be a ck function from M to N. Now, based on this discussion over here, what I'm going to write really is an if and only if, but I'm going to write it only one direction. If, OK, this is an important assumption. For now, you can think of it as a technical assumption. If the underlying spaces, vector spaces, E and F, are Banach, that is to say, if they are complete as metric spaces, and what else do I want? I want the necessary condition. F prime at x is invertible with a bounded linear inverse. Is invertible with a bounded linear inverse then I'm going to say, well, there are two open sets. Let's call them M tilde and N tilde of x and f of x. M tilde, I want to be a neighborhood of the input point that I chose, x. And I want N tilde to be a neighborhood of the output. And I want a phi ck function from N tilde to M tilde such that this happens. And there's a unique phi ck function from N tilde to M tilde such that for any, let's say, y bar in N tilde, if I feed phi of y bar into f, I get back what I fed initially into phi. Okay, that's the rigorous statement of the inverse function theorem that I'm interested in. Now, a faster way of saying the same thing would be to say, if f prime of x is invertible, then f is a local ck diffeomorphism near x. That is to say, it is an inverse that works as an inverse only near x. Right? That's sort of the phrase you would use. So ck diffeo near x. And like I said, these are in fact ephemeral Inv. So that means that from the perspective of differential calculus, a function is invertible in the sense of calculus, so it's a diffeomorphism. If and only if it is infinitesimally invertible. Its derivative is invertible. Okay. And what is more, why is this important? Well, you start with a function that is 5 times differentiable, let's say. You want to solve for x bar, but you want that function to be as regular as possible, ultimately. You want that function to be very regular. And so this is sort of the best possible situation. And really, this goes even further. If you had started with a real analytic function, for instance, a function f that has power series that converge, the solution would be also real analytic and stuff. But we're not going to get there because we're not really focusing on real analytic stuff in this class, even though you sort of looked at some situations. Any questions about the statement? It's a mouthful, and that's why I first stated the problem. If you understand the problem, you'll basically will be able to come up with what the inverse function theorem should allow you to do, ultimately. OK? Now let's state the implicit function theorem more rigorously. And this is sort of the scheme, right? So we started with the sort of vague interpretation, and this is like one way of sort of making it rigorous. I'm basically going to follow the same idea. Let k be a positive integer or infinity. Oh, now what do I want? I want the input space to be a product space. So I'm going to write it like so. Input space, let's say, has a horizontal component E1 and a vertical component E2. OK? I'm going to change the notation just a little bit. Let's say that M2 is of the form M1 times M2, Mi an open subset in Ei. This is just for convenience. In the proof, it becomes easier to write. So that means that ultimately, I want to think of my neighborhoods not as balls, but as rectangles. That's what you should think. Ultimately, it really doesn't matter. And let's take an input point, x, which is x1, x2. In M. This means that x1 is in M1, x2 is in M2. And so here I wrote xy. Here I'm writing for the same thing, x1, x2. OK? Let's let f to be a ck function from M to N. OK? If E and F are complete, and the necessary condition, which is this, then I should be able to solve, right? That's the idea. If E and F are complete, and the necessary condition, which is d2f at x. X is a tuple here. So instead of writing xy, I can just write x, is invertible. Okay. Then there is an open subset m1 tilde of m1 that contains x1. Okay. Did I write it over there? Yes, okay. m1 tilde that contains x1 and a unique ck function from m1 tilde into the second component, you see, because I want this to be a function of this. M2 such that for any x1 bar in m1 tilde, f of x1 comma phi of x1 in bars equals f of x1, well, f of x. And of course, I need to make sure that the initial condition is satisfied also. Okay. So it's longer to state implicit function theorem. When I first started learning this stuff, I really didn't like implicit function theorem. It was like more and like I had to use this, second partial and stuff like that. But I like this one more. Perhaps it's sort of easier to remember, but ultimately that becomes, in general, more useful as far as I'm concerned, in my experience. And so here we summarized the inverse function theorem by saying f prime of x is invertible if and only if it has a local ck diffeomorphism near x. Well, we can summarize the implicit function theorem in a similar fashion. We could say, well, the level set f equals f of x, so x is fixed, f equals f of x is a level set, is locally the graph of a function that is ck. That's what you can remember. So to functions you can associate certain subsets, like we did in problem set 1, I think. That is to say, you could take a function, you could look at the graph of the function. And implicit function theorem is sort of going backwards. You look at a certain subset of the product space, and you realize certain parts of the set can be represented as the graphs of functions. That's the idea. Where do I want to summarize this? Let's summarize it here. So invertible if and only if f equals f of x. So here there's the input. So this is a level set. Is the graph of a ck function near x. That's how we could summarize the implicit function theorem. Okay. Now, an important point. Again, this was something that I really disliked when I was first learning this stuff. Like, why do we need to take these smaller subsets? Why is this a local inverse? Why is phi only defined near this point that we're given? Likewise here. I mean, I kind of gave you a picture. Let me give you different ideas. First of all, from the perspective of differential equations 2, you should expect the solutions to exist uniquely only for nearby values compared to the initial condition. Okay? The solution existing globally is a different matter. It's a more complicated matter. That's first. Second, if you go back to your 3210 notes, there's an implicit inverse function theorem there. But there's a version of it that is global. It says, for instance, that if you have a function global inverse function theorem in 1D says, for instance, if you have a differentiable function, ck function, well, okay, from I to j, and if the derivative of this is never 0, then in fact it has a global inverse. So this is a diffeomorphism. You don't need to take this open set or open interval, whatever. So global diffeo if and only if f prime of x is not 0 for any x in I. Okay? Just to give you an idea as to how you could do this, well, those of you who have taken 3210 from me know that even for just differentiable functions, f prime has a certain property, namely this intermediate value property. So f prime cannot jump in one dimension from positive to negative, for instance. Which means that if f prime is never 0, that means that it's always positive or it's always negative. That is to say, f prime is either strictly increasing or strictly decreasing. Okay? Then you can imagine how we can sort of start building this global inverse. In multivariable, this is almost never correct. There is almost never a global inverse. At least, there could be, but inverse function theorem by itself often would not give you that global inverse, even if there exists one. It would always give you, almost always give you, a local inverse. Now, it turns out that there is a global inverse function theorem in multivariable calculus, but it requires more assumptions. Okay? I'm not going to say what those assumptions are. I'm just going to give you the name. So, global inverse function theorem in multivariable. You should look out for Adamar theorem. Great mathematician. Basically, the assumption is, so the extra assumption you need is that f, let me put it this way. If you were to take a compact subset in the output space, you want the pre-images of that compact subset under f to be still compact. We had discussed how the forward images of compacts are compact under continuous. Now you're asking for the backward direction, which kind of makes sense because you're trying to come up with the inverse. Okay? So the extra assumption is what is called properness. Proper is one of those words that get overloaded in math. You have other phrases like this: normal, regular, whatever. This is one of them. Okay, just letting you know, there are global versions, but we're not going to discuss that. Remember, I was mentioning how in this class we are really focusing on the local theory. I thought, even though we could do it, it's not significantly complicated compared to this theorem. It's not thematic, so I decided to let it go. But you should know of its existence. Okay. 15 minutes. I'm debating if I want to mention something. Okay, I'm not going to mention this. Okay. Those of you, let me just say this. Those of you who are interested in these kind of things, related to these types of ideas, is this open problem. So it's a problem that no one knows how to solve in complete generality, which is called the Jacobian conjecture. You look at this inverse function theorem. It says that if f is ck, k times differentiable, whatever, its inverse too, the local inverse, has the same property. And then you say, oh, if I started with an infinitely many differentiable function, the inverse too has the same property. And I told you that the same thing holds when it comes to real analytic functions too. What is better than real analytic? Well, polynomial. You want to say something like, if f is a polynomial function, I want the inverse to be polynomial as well. That's the conjecture. Let me write it. I just learned that the existence of this in like 2 weeks ago. So Jacobian conjecture. Let's say f is a function from Rn to Rn. Okay. Let's say it's a polynomial function. In fact, let me say not only that f prime exists or invertible. In fact, in this case, I can think of f prime as an n by n matrix, which means that I can look at the determinant of it to talk about its invertibility. Let me just say for any input x, determinant of f prime of x is 1. It's a constant function. So if for any x in Rn, determinant of f prime of x is 1, then f inverse is a polynomial. It exists and is a polynomial. This is, you see, one of those problems that look very simple, and you should be scared of problems that look simple. Okay? That means that even I am at that stage. I look at this and I feel like we should have been able to solve it like 50 years ago. Which means that there's something very complicated going on underneath all this. For degree 2 polynomials, as far as I understand, this is solved. And if you can solve it, for instance, in general, you would be done for the rest of your life. You would have sort of job security, whatever. People would leave you alone. Okay. Okay, that's that. Back to reality. Let's talk about how inverse function problem and implicit function problem are really the same thing. Okay. So I had started talking about this on Wednesday. I want to assume that I can solve the implicit function problem. And based on this assumption, I would like to verify that indeed I can also solve the inverse function problem. Okay. Imp.F.T implies Inv.F.T. I'm going to use this more vague notation, and I'm going to leave it to you to do the same thing using the formal statements. So do formally. Do the same thing with the formal statements. Do the same with theorems. I look at my givens, and I'm assuming that f prime of x is invertible also. What I want to do is solve this. what did we do? Well, we package what we were trying to do in terms of what we assume we can do. Okay? So I'm going to define a capital F. Okay? And what is this going to be? It's just going to be lowercase f applied to x bar minus y bar. And I'm defining z to be 0. Okay? And so what I'm trying to do within the paradigm of the inverse function problem turns into, within the paradigm of the implicit function theorem, to solve for capital F equals 0. Okay? So have solve this for, instead of y bar, I want to display x bar as a function of y bar, which means that I want to solve this for x bar. What is the necessary condition? If I'm trying to solve for y bar, I need the corresponding partial to be invertible, which means that there I need really the x partial, or the first partial of capital F, to be invertible. But certainly the x partial of this is nothing but f prime. Which I had assumed to be invertible. Which means that within the paradigm of the implicit function theorem, this has a solution. It has a unique solution. There's a unique phi such that x is a function of y, and capital F applied to this is at the same height. And certainly, the initial condition is satisfied also, so that I have this. But if phi is such that this happens, going back to the original definition, this means that this is true, which is what I wanted. Okay? Oh, sorry. Five minutes? Good. Any questions about this? I highly recommend you go over the problem by yourself, really understand how I came up with this necessary condition. Those are important things. It's more important than the theorem. Understand the problem. If you can understand the problem, then you can remember this problem I can solve, okay? This is also important. If I can solve this problem, I can also solve this problem. That's what I did here. Now going the other way around, I want to also verify that if I can solve the inverse function problem, I can solve the implicit function problem. This is slightly harder, but it's not significantly harder compared to that. So this time, Inv.F.T, or Inv.F.P, maybe, implies Imp.F.T. Now this time, I'm given f, x, y, and z, and I also have the necessary condition. Somehow I need to package these. I still have juice in the battery. So I have this, and I have this. Somehow I want to compile these two red boxes into something that I could recognize within the paradigm of the inverse function problem. Okay. See, this is slightly harder. Again, I'm going to use capital F for this new function I'm going to define. I'm going to write it in such a way that it looks like it takes two inputs, but I'm going to think of it as one input in sort of like a space that has two components. Okay. Define this. Okay. Now, what did we do? So capital F at xy, right, now is equal to x comma f of xy, but I had assumed that this second component is nothing but z. So this is this. Let's now compute the derivative like we did over there at this point. Well, this could be in principle sort of like an abstract space, but I can imagine this to take two inputs and two outputs, and I can write therefore f prime as a 2x2 matrix where each entry is a bounded linear operator. Okay, so I'm just going to take this function, differentiate. This is the first component, differentiate with respect to x, just identity. With respect to y, 0 transformation. Differentiate with respect to x. Horizontal partial of f, differentiate with respect to y, vertical partial of f. Now I claim that insofar as I assume this, that the second partial of lowercase f is invertible, so is this uppercase f prime. How do you do this? Well, you set up this equation. I'm going to leave it to you. Just pretend that everything you can do with matrix algebra, you can do in this situation as well. PQRS. Well, what does it mean for this guy to be invertible? There should be another 2x2 such that when I multiply, I get the identity transformation. Okay. This equation gives you 4 unknowns in terms of operators, right? So this by this and so on. So P has to be I. This by this should be this, which means Q has to be 0. This by this plus this by this should be 0. Times R is 0. This by this times this plus this by this should be 1, or identity. It's 2. S is identity. So this is a system of 4 equations with 4 operator unknowns. I'm going to leave it to you to solve and see that this is invertible, and then complete this transformation of this into this or this into this, whatever. Okay, this is how we sort of relate the two. We're done with the heuristics. On Monday, at least, I would like to discuss items of the proof. Thank you.